Somewhere inside your head right now is about 1,300 cubic centimeters of the most complicated material in the known universe. Your brain. And here is the quiet, slightly unsettling fact that this whole video is about. The humans who lived roughly 30,000 years ago had bigger brains than you do. Not metaphorically, not as a figure of speech. Measurably, physically, on average, larger skulls holding more brain volume than the people alive today. Our ancestors were, in a very literal anatomical sense, bigger brained than us. Now, before you spiral, because that sentence has a way of landing wrong, this is not a scare story, it is not a decline of humanity story. It is not any of the things that phrase tends to get twisted into on the internet. What it actually is one of the most genuinely interesting open questions in paleoanthropology right now. Real scientists, real measurements, real disagreement about what any of it means. And that last part, the disagreement, is kind of the whole point. Because here is what I find so fascinating about this. We have the data. We can measure ancient skulls. We can calculate volumes with reasonable precision. The shrinkage appears to be real, on the order of about a tennis ball's worth of tissue lost over thousands of years, which sounds dramatic until you sit with the actual numbers and the actual debate around them, and then it gets complicated in the most interesting way possible. Some researchers think the timing points to the rise of agriculture and the dietary shifts that came with it. Others think it has everything to do with something called self-domestication, the idea that as human societies became more cooperative and less individually violent, the brain changed shape and possibly size in ways that mirror what we see in domesticated animals. Others still think the brain did not really shrink in any meaningful functional sense at all, just reorganized, compacted, got more efficient the way a newer phone has a smaller chip that does more than the old one. And then there is the wildest hypothesis, the one that involves ant colonies, that we will absolutely get to because it deserves its own moment. So that is the roadmap tonight. We are going to start with the evidence, what we actually measure and how, because the methodology matters enormously here, and a lot of the headlines skip straight past it. Then we are going to walk through the timeline, when the brain was at its largest, when the decline seems to begin, and what varies across different populations and regions. Then we get into the explanations, and there are several, and they are genuinely competing, and scientists have not settled on one. And finally, we are going to sit with what this means, and what it does not mean, which might be the most important part of all, because the honest answer to the title of this video, the reason no one can fully explain it, is not that we are stumped in some hopeless way. It is that the evidence points in multiple directions at once, and the people who study this for a living are still working it out. That is science, doing what science actually does, which is messier and more interesting than the version where everything is already answered. If you are listening to this right now, which you clearly are, I would love to know where you are and what time it is for you. Drop it in the comments. This channel has always had something I find genuinely lovely about it. People from Berlin at breakfast, and Boston at 2 a.m, and somewhere in New Zealand what I can only assume is an unreasonable hour. All listening to the same quiet story about very old skulls. It makes the whole thing feel less like broadcasting and more like a conversation. And if you're on Spotify, there's a follow button with my name on it. Following there is one of the best ways to support what I do, and you get the episodes completely ad-free with no background music, just the voice. The link is in the description if you need it. One more thing before we actually get into the skull measurements. There is a book over at sleepytimehistory.com that goes deeper on some of the evolutionary stories this channel covers, and there is a discount running this week if you're interested. I will mention it again later, but if you are the kind of person who wants to read the longer version of these nights, that is where it lives. Alright, so your skull is a little smaller than your great times 1,000 grandmother's skull. Maybe, probably, under certain assumptions with certain measurement techniques, accounting for certain variables, that hedging is not weakness. That is exactly the kind of precision this topic deserves, because the moment you strip the nuance out of human evolution, you end up somewhere much less interesting than the truth. Let's start with what we actually mean when we say brain size, because it is a more complicated question than it sounds, and the answer changes everything that comes after it. When scientists talk about brain size in the context of ancient humans, they are almost never talking about actual brains. Brains do not preserve. They are soft tissue, roughly 78% water, and they decompose quickly after death. What survives is bone. So, when a researcher tells you that a Pleistocene human had a larger brain than a modern one, what they have actually measured is a skull, specifically the internal volume of that skull, a number called cranial capacity. Cranial capacity is measured in cubic centimeters, and it represents the space inside the brain case, the part of the skull that houses the brain. You can estimate it a few different ways. The oldest method involves filling a skull with something small and uniform. Mustard seeds historically, sand or small ball bearings, then pouring that material out and measuring the volume. It works, roughly. The more modern approach uses CT scanning to build a digital model of the interior and calculate volume computationally, which tends to be more precise, but introduces its own assumptions about how you handle the landmarks and boundaries. Either way, you end up with a number in cubic centimeters, and from that number you make an inference about how large the brain inside probably was. And there is the first important caveat. Cranial capacity is a proxy. It is not a brain measurement. It is a skull measurement. The relationship between the two is real and strong. Brains do fill their cases quite well, but it is not perfect. The brain is surrounded by membranes, by cerebrospinal fluid, by blood vessels, by connective tissue, and all of that takes up some of that internal space too. So when you say a skull had a cranial capacity of 1,500 cubic centimeters, you are not saying the brain was 1,500 cubic centimeters. You are saying the total contents of that brain case were, and the brain was the majority of it, but not all of it. There is also the issue of what happens to bone over thousands of years. Skulls distort, they compress under sediment, they dry out and crack, and get reassembled from fragments by researchers doing their best with what they have. Measurement error on ancient specimens can run to several percent, which matters when the differences you're trying to detect are themselves only a few percent. The error bars on a single ancient skull can be quite wide, which is part of why the science here relies on population averages, not individual specimens. You need a lot of skulls from a lot of places and a lot of time periods before any trend starts to emerge with real confidence. That brings us to a distinction that is easy to miss, but changes the entire framing of this conversation. There is absolute brain size, which is just the raw volume, and there is relative brain size, which is brain volume scaled to body size. These are different measurements, and they tell you different things. A sperm whale has an absolute brain size of around 8,000 cubic centimeters. That is roughly 5 times the size of a human brain. And yet we do not generally think of sperm whales as 5 times smarter than us, whatever smarter even means, because most of that extra brain tissue is doing the work of running an enormous body. The bigger the body, the more neural tissue you need just to manage basic functions, sensation, movement, organ regulation. So when you want to compare cognitive capacity across species, you need to account for body size, and the standard way of doing that is with a measure called encephalization quotient, or EQ. It describes how much larger or smaller a brain is relative to what you would predict for an animal of that body size. Humans have an exceptionally high encephalization quotient. Our brains are far larger than you would expect for a mammal of our size, which is part of what makes us unusual, but here is where it gets relevant to our story. When researchers track the apparent decline in cranial capacity over the last several thousand years, they are looking at absolute size, and body size has also changed over that same period. Average human stature and body mass have fluctuated quite a bit across populations and time periods, and if body size and brain size are shrinking together and at similar rates, the encephalization quotient might not be changing much at all. Some researchers think this is actually what is happening. The brain has gotten a little smaller because the body has gotten a little smaller, and the scaling relationship has stayed roughly intact. Others disagree and think the brain has shrunk faster than the body, meaning encephalization itself has declined slightly. This is an active area of disagreement, and the answer depends partly on which populations you measure and over what time frame. The claim at the centre of this conversation is specifically about population averages changing over time. It is not a claim about any individual. It is not saying you personally have a smaller brain than a specific ancient ancestor. It is saying that if you calculated the average cranial capacity from a large sample of modern human skulls and compared it to the average from a large sample of skulls from populations living roughly 20,000 to 30,000 years ago, you would find the older group had a higher average. That is a statistical trend across many individuals, not a measurement of any one person, and it is a trend that comes with real uncertainty, because the ancient samples are always smaller, always less geographically complete, and always subject to the preservation and measurement issues we just talked about. The magnitude of the difference, the number you will see quoted most often, is roughly 10%. Average cranial capacity in modern humans sits around 1,300 to 1,350 cubic centimeters, give or take, depending on the population and the study. Some estimates for the Pleistocene peak run to around 1,500 cubic centimeters or slightly higher. The difference between those two numbers is somewhere in the range of 150 cubic centimeters, and that is approximately the volume of a standard tennis ball. Now, a tennis ball sounds significant when you frame it as tissue that used to be there and is no longer there. It sounds less significant when you remember that individual variation in modern brain volume runs to several hundred cubic centimeters in either direction, and that brain volume across modern humans alive today already spans a range that makes that 150 centimeter difference look modest. A completely neurologically typical person can have a brain of 1,100 cubic centimeters or 1,600 cubic centimeters and function the same way. So the population average shift, while real and worth investigating, is not enormous relative to the natural range. The most important thing to say clearly, and this cannot be said clearly enough, is that cranial capacity does not measure intelligence, not even approximately, not even as a rough proxy within our own species. The history of science is full of researchers who tried to use skull size to rank human groups, and it is an ugly history that produced consistently wrong results, because the underlying premise was wrong. Brain organization, neural density, the efficiency of connectivity, the structure of specific regions. These are what matter for cognitive function, and none of them show up in a skull volume measurement. A number of modern researchers studying the brain size decline are quite careful to say exactly this, and it is worth holding on to as we go deeper into the explanations, because some of those explanations are genuinely surprising, and a few of them suggest the brain may have become more capable even as it became physically smaller. But we are getting ahead of ourselves. Before we get to explanations, we need to understand what the measurements actually show. When was the brain at its largest? What does the timeline look like? And how do scientists reconstruct that timeline from fragments of bone that are tens of thousands of years old? That is where we are going next. If you want to understand whether brains used to be larger, you first have to do something surprisingly tricky. Build a dataset of ancient heads. Over the last century and a half, scientists have used a whole toolkit to turn old skulls into numbers. The earliest approaches were very physical. You take a skull, seal the little holes at the base as best you can, and pour in something fine and uniform. Historically, that was mustard seed or lead shot or glass beads. You tap the skull gently so everything settles, pour the contents back out into a graduated cylinder, and read off the volume. It's ingenious, and it gets you into the right ballpark. But it's also sensitive to every wiggle of the hand and every tiny crack the filler can leak through. Different people might get slightly different numbers on the same specimen. Mustard seeds don't flow quite like water, and they definitely don't flow like living tissue. Later, people switched to water displacement. You place the skull in a container, track how much the water level rises, and from that, infer the volume it displaces. There are methods where you cast the interior with plaster or silicone, then measure the cast instead. Each step forward makes the procedure more standardized, but every step also adds assumptions. Where exactly does the brain case end and the face begin? How do you handle a skull that's missing bits? Today, the gold standard is digital. You CT scan the skull, creating a stack of high-resolution slices. Software then traces the inner surface of the brain case and integrates across all those slices to calculate a volume. This is called volumetric analysis, and it can be astonishingly precise when the skull is well preserved. It also lets you do things the old methods never could, like virtually fill in small missing areas using mirrored anatomy from the other side. But even CT scanning can't conjure bone where none remains. And that brings us to the first big scientific headache. We almost never have perfect skulls. The fossil and archaeological record is fragmentary by nature. Skulls crack in the ground, they get crushed under sediments, they're chewed by animals, washed away by floods, or simply never buried in a way that favours preservation in the first place. What survives tends to be a biased sample, robust bones from caves and dry shelters, often from particular regions where conditions are kind to bone. So when you see a plot of cranial capacity over time, you're not looking at a complete census of ancient humanity. You're looking at the subset of individuals who happen to die in exactly the right place, whose bones survived long enough to be found, and whose skulls were intact enough to measure. That's preservation bias. On top of that, there's geographic skew. Europe and parts of the Near East are heavily sampled because they've been excavated for centuries and have lots of caves. Large parts of Africa and Asia, where enormous pieces of our story unfolded, are still undersampled, or their fossils have not yet been discovered. Sampling issues like these are not flaws in the honesty of the science. They're just the reality of working with deep time. Paleoanthropology lives with uncertainty, the way sailors live with weather. You don't get rid of it, you learn how to navigate it. Another layer of complexity is dating and context. A skull is not very informative if you don't know when and where it came from, or who it belonged to in the broad sense of population. Sometimes the dating is straightforward. If a skull is found in a well-stratified cave layer with volcanic ash above and below, you can use methods like argon, or radiocarbon dating of associated material to pin down an age range. Other times, it's trickier. A skull might be found in disturbed sediment or collected decades ago with sparse notes about precise location. In those cases, researchers have to cross-check the style of stone tools found nearby, the fauna in the layer, the chemistry of the bone itself. Assigning skulls to populations is another careful inference. You might have genetic data from a tooth, which is ideal, or you might rely on a combination of location, age, and skeletal features to say, this is likely an Upper Paleolithic European, or this is likely a late Pleistocene North African. All of those decisions feed into the final graphs showing how cranial capacity has changed within and between groups over time. Once you've got measurements, dates, and context, you still need statistics. Brains, like height, cluster around an average, but that average is only part of the story. There is always a range. Imagine you have 10 skulls from a site dated to 25,000 years ago. Their cranial capacities might run from 1,250 to 1,750 cubic centimeters, with most clustering around, say, 1,500. Then you take a modern sample of a few hundred individuals and find an average closer to 1,350, with a similarly wide spread. Those overlapping ranges mean that some ancient people had smaller cranial capacities than many modern people, and some modern people have larger capacities than many ancient ones. The trend lives in the averages, not in any single specimen. This is why single dramatic skulls can be misleading. A giant-brained individual from one cave doesn't tell you the whole story of their population any more than a 7-foot-tall basketball player tells you the average height of modern humans. What matters is sample size, the spread of the data, and how confident you can be that the difference you see isn't just random noise. And that, in turn, helps explain why different research papers can report different numbers without anyone lying or cooking the books. One study might focus mostly on European Upper Paleolithic skulls from well-studied caves and get a high average cranial capacity. Another might include more samples from later, warmer periods, or from different regions with slightly smaller body sizes and get a lower average. Some researchers use only CT-derived volumes. Others rely on older mustard seed-style measurements, converted with correction factors. Some include certain borderline specimens, others exclude them for being too fragmentary. Change the recipe, even slightly, and the exact numbers can shift. One team might say the peak average was 1,500 cubic centimeters. Another might argue for 1,450. One group might place the onset of decline around 30,000 years ago. Another, like Jeremy De Silva's team, might suggest a more recent timing closer to 3,000 years ago, based on a different way of binning and modelling the data. These are not signs of deception. They are what it looks like when scientists push blurry data as far as it can reasonably go, and argue in good faith about where the blur stops and the pattern begins. This is also a good moment to mention something quietly delightful. If you enjoy wandering through these long arcs of human history in a calm, unhurried way, there's a book on sleepytimehistory.com that goes much deeper into how we know what we know about the deep past. There's a discount running there this week, if that sounds like your kind of bedtime reading. For our purposes, the takeaway is simple. When you hear that human brain size peaked in the late Pleistocene and has declined since, remember the scaffolding under that statement. Mustard seeds and CT scans, broken skulls painstakingly reconstructed, patchy geographic coverage, cautious statistics. The trend is built not on certainty about any one skull, but on patterns that keep reappearing when you look across many skulls, many sites, and many methods. With that framework in place, we can finally ask, when in this flickering record of bone and sediment does the human brain seem to reach its greatest average size? And what happens after that peak? When you line up all those measurements in time, with all their caveats and blurry edges, a pattern still emerges. Somewhere in the late Pleistocene, especially during what archaeologists call the Upper Paleolithic, average human cranial capacities seem to reach their highest point. Not at the very beginning of our lineage, not in some distant proto-human past, but relatively recently, geologically speaking. Roughly between about 40,000 and 20,000 years ago, for many well-sampled regions, you see populations whose average brain volumes are a bit larger than what you find in most modern samples. Upper Paleolithic sounds technical, but you can think of it as the last great Ice Age chapter before the world warms into the Holocene. Glaciers are sprawling across much of northern Europe and North America. Sea levels are lower. Environments are harsh, seasonal, and often cold, especially at higher latitudes. This is the time of elaborate bone and antler tools, of cave paintings in Europe, of complex hunting societies in Africa and Western Asia. It is also the time of some very big-bodied, cold-adapted humans. Cold climates push bodies in a particular direction. To conserve heat, selection tends to favour stockier builds with shorter limbs and larger trunks. That same logic applies across other mammals too. Arctic foxes are rounder than desert foxes, reindeer are more compact than tropical antelopes. Humans living in glacial Eurasia were no exception. Their skeletons, when we find them, often show broad chests, powerful limb bones, and overall body masses higher than those of many present-day populations. Brains scale with bodies. A larger animal generally needs a larger brain simply to manage a larger organ system. More muscle to coordinate, more tissue to regulate, more sensory input to process. So when you look at those big Upper Paleolithic skeletons, Part of their large cranial capacities is just that basic scaling. If you took an average modern human body and resized it to match one of those robust Ice Age hunters, you would expect the brain volume to go up somewhat, even without any change in intelligence as we colloquially think of it. This is why anthropologists are careful to talk about brain size relative to body size, not just raw volume. A 1,500 cubic centimeter brain in a very large, heavily muscled body is not necessarily more in functional terms than a 1,400 cubic centimeter brain in a smaller, lighter body. One reason the Upper Paleolithic looks like a peak is that we are disproportionately sampling large-bodied, cold-adapted people from cave environments that preserve bones well. But even if you adjust for body size, something interesting remains. Many of these late Pleistocene groups still seem to have brains on the larger side compared with later Holocene populations occupying the same regions, even after you account for changes in stature and build. The effect is not enormous, and it overlaps a lot, but on average the curve in many studies does tilt downward after this period. It's important, though, not to imagine a single golden brain size that all Upper Paleolithic humans shared. The variability we saw in the previous section is very much present here. Some individuals have cranial capacities well within the modern range. Others are at the upper tail of what we see in any Homo sapiens. Different regions show different averages. A large brain sample from one European cave is not a template for all humans alive at that time. Any more than one modern city is a stand-in for the whole planet today. And this isn't just a story about our species. If you widen the lens to include other members of the genus Homo, the picture becomes even less like a simple ladder. Neanderthals, for instance, often had brains that were as large as, or larger than, those of Upper Paleolithic modern humans. Again, in part because they were heavily built and cold-adapted, but also because their brain organization and life history were tuned to their own ecological niche. Earlier Homo heidelbergensis and some late Homo erectus had smaller average brain sizes, but there is overlap there too. The trajectory from Homo erectus to Neanderthals and modern humans is not a smooth, monotonic climb. It's more like a branching bush with different lineages experimenting with different combinations of body size, brain volume, and behavior. There were even contemporaneous humans with smaller brains. Late surviving Homo floresiensis in Indonesia, for example, had very modest cranial capacities compared with us, yet left evidence of sophisticated behavior relative to their size. The same is true for Homo naledi in South Africa, whose brain volumes were closer to earlier Homo, but whose possible burial behaviors and hand anatomy suggest complex, perhaps symbolically rich lives. Big brains are not automatically better, and they do not always move in one direction over time. So when we say that late Pleistocene Homo sapiens reached a peak in average cranial capacity, we're talking about a local high point along one branch of a very bushy tree, not the top of a cosmic staircase. It's a peak defined by particular climates, particular bodies, particular ways of making a living. And this is where the mystery begins to sharpen. Because if you follow those Upper Paleolithic populations forward into the Holocene, the warmer, more stable epoch that begins around 11,700 years ago, the general direction of change in many data sets is not up, but down. As glaciers retreat and climates moderate, as some groups settle, domesticate plants and animals and reshape landscapes, average cranial capacities in several regions seem to decline. That reversal is what has caught so much scientific attention. For millions of years across the broader Homo lineage, the long-term trend has been toward larger brains with fluctuations and side branches along the way. Then, after this late Pleistocene high, our own species appears to bend the curve back on itself. Not catastrophically, not uniformly, and not everywhere at the same time, but enough that, on those graphs built from mustard seeds and CT scans, the line tilts. What changed between those Ice Age hunters and us? Why would a species that had invested so heavily in an energetically expensive organ start, on average, to carry slightly less of it. And why does that shift seem to happen just as humans are inventing agriculture, building larger societies, and weaving denser networks of culture and technology? To explore that, we need to watch the world warm, the ice melt, and human ways of life transform. That's where the decline begins. If you try to put a single pin in the calendar and say, the decline starts exactly here, the evidence immediately pushes back. Instead of a sharp cliff, what we see between about 30,000 and 10,000 years ago is more like a long rolling hillside. In some places, the slope starts to tip a bit earlier. In others, it's later. Different researchers draw slightly different curves depending on which skulls they include, how they estimate volumes, and how they correct for body size. But across a lot of independent data sets, that broad late Pleistocene to early Holocene window is where the average begins, quietly, to lean downward. Part of the difficulty is simply numbers. The further back you go, the fewer skulls you have, and the more each one matters. A single large or small specimen can tug a regional average up or down, especially for time slices where we only have a handful of individuals. Add in the fact that dates can be uncertain by hundreds or even thousands of years, and the idea of a precise start date starts to look more like a mirage. So instead of a single turning point, it's more honest to think in terms of overlapping trends. In Europe, for example, some studies suggest that the biggest Upper Paleolithic cranial capacities appear between about 30,000 and 20,000 years ago, with a gentle decline starting by around 15,000 years ago and continuing into the Holocene. In parts of the Near East, where people begin to cluster in more settled communities a bit earlier, apparent reductions show up slightly sooner. In sub-Saharan Africa, the record is spottier, but several lines of evidence point to a similar pattern unfolding on its own schedule. Even within the same broad region, it's not synchronized. A population living on the open steppe, hunting large game at the height of the last glacial maximum, may look different from a population sheltering in milder refuges along coasts or river valleys, even if they are separated by only a few hundred kilometers. As ice sheets retreat and ecosystems rearrange themselves, groups move, mix and split. What looks like a single population in our graphs is often a tangle of lineages passing through the same general area at different times. This is why different teams sometimes publish different timelines. One well-known analysis led by Jeremy De Silva and colleagues, for instance, argued that the major drop in human cranial capacity begins surprisingly late, only around 3,000 years ago, based largely on European archaeological samples and museum collections. That claim sparked quite a bit of debate, in part because other researchers see earlier declines starting shortly after the last glacial maximum, long before classical civilizations appear. When critics dug into the details, they pointed out that the De Silva dataset was heavily weighted towards certain regions and types of skulls, and that the choice of which fossils to include, how to handle sex differences, and how to group time periods can all shift where the line seems to bend. Follow-up work using broader and more globally distributed samples tends to push the beginning of the decline back into that 20,000 to 10,000 year range for many populations, even if there may also be more recent shifts layered on top. So we're left with a picture that is both frustratingly fuzzy and surprisingly consistent. Fuzzy because we cannot say, on this exact date, humans everywhere started shrinking their brains. Consistent because when you zoom out and look at long-term averages, multiple independent studies find that late Pleistocene Homo sapiens in several regions had slightly larger mean cranial capacities than their Holocene descendants. The key phrase there is in several regions. This is not a global lockstep transformation stamped onto humanity all at once. It is a pattern that shows up with local accents as the world warms out of the Ice Age. There's another layer of complexity that anthropologists have to deal with. Who exactly is being measured at each point in time? If you look only at raw skull sizes through time, you might think you're watching a single population evolve. But past landscapes were full of movement. As climates changed, some groups stayed put and adapted. Others migrated in from elsewhere. Still others disappeared entirely, replaced by newcomers whose bodies and brains were already somewhat smaller or differently shaped. Imagine tracking average height in a modern city that over a few centuries receives waves of migrants from many different regions. The numbers would shift, but not because people already living there were evolving dramatically taller or shorter in a few generations. Instead, the mix of ancestry would be changing. The same thing can happen in the fossil record. A shift from big, cold-adapted hunters to more gracile, warm-climate farmers in the same valley might look like an evolutionary downsizing, when in reality it could be a population replacement or a blend of evolution and replacement together. Demography matters in other ways too. Age and sex ratios, for example, can skew averages. If an archaeological sample from one period is mostly robust adult males, and a later sample from the same region includes more females and adolescents, the second group will almost certainly have smaller average cranial capacities, even if there is no evolutionary change at all. Researchers use various statistical tools to try to untangle these effects. They standardize for sex where possible. They estimate body size and correct for it. They separate clearly distinct populations when the data allow. Even so, there is always the possibility that some of the downward tilt we see in the graphs is being produced by changing population structure, not just by natural selection acting on brain volume directly. This is why, in this episode, we'll keep returning to a careful distinction. One level of the story is rock solid. Relative to those late Pleistocene high points, many Holocene populations, especially after the rise of agriculture, show smaller average cranial capacities. That broad decline shows up across multiple continents, using different measurement techniques, and it lines up reasonably well with big shifts in how humans lived. Another level, the exact timing of the first bend, the contribution of migration versus in-place evolution. The role of body size changes is still under active debate. Different teams draw slightly different lines through the same cloud of points. Their disagreements aren't about whether any decline exists, but about when, where, and how it played out in detail. As we move into the Holocene, this is also the moment when many of the themes that run through this channel start to intertwine. Self-domestication, the rise of agriculture, shifts in social complexity, changes in diet and disease environments, all of them are getting underway, or accelerating during this same broad window. If you enjoy sinking into these long, slow puzzles, by the way, this is exactly the kind of deep time storytelling we explore in more detail in the book over at sleepytimehistory.com. There's a discount this week if you'd like something gentle and evidence-rich to fall asleep to after this episode. For now, though, we'll keep our focus on the skulls. The world is warming. People are experimenting with new ways of living. And, somewhere in that stretch from the last ice age into the Holocene, the average human brain case begins, quietly, to shrink. Next, we'll ask, how big is that drop, really? And is it as dramatic as some headlines make it sound? So how big is this change that everyone keeps talking about? If you skim headlines or popular science books, you'll often see one number, about 10%. The claim is that compared to their late Pleistocene peak, average human brain volumes have fallen by roughly a tenth. As a first, very rough summary, that's not totally unreasonable. Many studies that focus on Upper Paleolithic hunter-gatherers in Europe and parts of Western Asia report average cranial capacities in the ballpark of 1,450 to 1,500 cubic centimeters. Typical modern human averages today, depending on region and sample, hover closer to 1,300 to 1,350 cubic centimeters. That's where the about 10% line comes from. Not from a single definitive data set, but from a cluster of overlapping estimates that all suggest a modest downward shift. The temptation is to turn that into something like, we've lost a chunk of brain the size of a grapefruit, and then let your imagination do the rest. The reality is quieter and more finicky. If you take a drop on the order of 150 to 200 cubic centimeters and try to picture it, you are not looking at half a head disappearing. You're looking at something closer to a tennis ball's worth of volume. Not a literal ball sitting on top of the brain, of course, but a total difference in how much space the brain case encloses. Even that mental picture comes with caveats. First, those are mean values, averages constructed from many individuals over long spans of time. Second, they're typically reported for particular regions and particular time slices, not for ancient humans everywhere compared to modern humans everywhere. And third, the samples are not always matched for things like sex, body size, and age at death, all of which matter when you're talking about cranial volume. There's also the issue of overlap, which is where some of the scare stories begin to dissolve. When anthropologists plot cranial capacities from late Pleistocene populations and Holocene populations on the same graph, they don't see two neat, separate clusters with a clean gap between them. They see two broad clouds of points that overlap heavily. Some Upper Paleolithic people had relatively small brains by our standards. Some modern humans, especially large-bodied males, have cranial capacities right in the middle of the ancient range. If you lined up a group of Ice Age hunters and a group of modern city dwellers and measured only their brain cases, you would not be able to divide them perfectly into big-brained then and small-brained now. What changes is the center of gravity of those clouds. Imagine two hills of sand. One hill is centered slightly to the right, one slightly to the left. Most grains of sand are still clustered in the middle, and there's a lot of overlap. But if you calculate the exact center of each pile, one is shifted a little compared to the other. That's what these averages are picking up. Means can move even when the ranges are almost the same. You can see this in human height today. The tallest people in the world right now are not wildly taller than the tallest people who lived a few thousand years ago. The overlap is huge. But the typical person in the Netherlands, for example, is significantly taller on average than the typical person in the same region several centuries ago. Diet, health, and social conditions have nudged the center of the distribution upward, even though the extremes were always possible. The same statistical logic applies to brain size. You don't need every ancient person to have had a huge brain, and every modern person to have a smaller one, in order for the mean to drift down by 10%. You just need enough of a shift in the typical values over time. That said, we have to be careful about what's being averaged and how. Not all brain size measurements are created equal. Some skulls are measured by pouring tiny beads or mustard seeds into a cast of the brain case and then counting the displaced volume. Others are estimated from linear dimensions taken with calipers. More recent work uses high-resolution CT scans to reconstruct the interior of the skull in 3 dimensions. Each method has its own quirks and margins of error. When you start mixing them together across studies, you introduce extra noise. A decline of 50 cubic centimeters might evaporate entirely if 2 methods happen to be biased in opposite directions. A decline of a couple of 100 cubic centimeters that shows up across multiple methods and multiple regions is harder to explain away, but the exact numbers still wobble. Sex and age matter too. Male skulls are, on average, larger than female skulls, even within the same population. So a sample that is 80% adult males will look very different from a sample that is half female, or that includes more adolescents and older adults. Archaeological collections are rarely perfect cross-sections of living communities. They're shaped by burial customs, excavation biases, and sheer chance. Body size complicates things even further. Brains don't scale perfectly with body mass, but they do scale. Larger bodies tend, on average, to house larger brains. So if a region's people become smaller bodied over thousands of years because of climate, lifestyle, diet, or any of the other factors we'll explore later, you'd expect some reduction in average brain volume, even if the brain is keeping pace perfectly with the body. Some researchers therefore try to correct cranial capacity for body size using proxies like the dimensions of long bones or overall skull length and breadth. When they do this, the magnitude of the decline can shrink. In some analyses, the raw 10% drop becomes something more like 5 to 7% after controlling for stature and build. In others, a noticeable decline persists even after these adjustments. suggesting that there may indeed have been a change in relative brain size, not just in overall body scale. All of this means that the 10% figure is best treated as a convenient, rounded headline, not a sacred, unchanging fact. The underlying pattern, a gentle downward shift in average cranial volume from late Pleistocene highs into the Holocene, is robust enough to take seriously, but it sits on top of a thicket of measurement issues, overlapping distributions, and demographic complexities. It is not a clean story of big-brained ancestors versus small-brained moderns. Once you see the nuance, a different kind of question comes into focus. If the change is modest, if many modern people still fall well within ancient ranges, and if part of the shift is tied up with body size and lifestyle, then what exactly is being selected for? What changed about how our ancestors lived that made a slightly smaller, differently organized brain case a recurring outcome? To get at that, we have to look not just at how much the skull shrank, but where and when those changes show up most clearly. When you zoom out from individual skulls and look at maps, the picture gets even less tidy. The late Pleistocene big brain signal is strongest in places where we simply have the most fossils: Europe, parts of Western Asia, and a few well-studied regions of Africa. Many of the classic datasets that underpin the 10% drop are built from Upper Paleolithic Europeans transitioning into early Holocene farmers. That alone should make us cautious. If you mostly sample one corner of the Old World during one particular shift in lifestyle, you're more likely to see regional stories than a universal law of human biology. In Europe, for instance, several studies find a fairly clear pattern: large average cranial volumes in late Ice Age hunter-gatherers, a decline starting somewhere between about 20,000 and 10,000 years ago, and then a continued drift downward into the Neolithic and Bronze Age. That's the version that often gets reported as if it were the human story. But when researchers look at some African samples or at East Asian material, the timing can wobble. In parts of North and East Africa, for example, there are hints that cranial volumes stay relatively high well into the early Holocene, then taper off more gradually. In some East Asian series, the decline seems smaller or more stepwise, with periods of stability punctuated by sharper drops that track particular cultural or environmental changes. And in other regions, we just don't have enough well-dated, well-measured skulls to say anything confident at all. Big stretches of South Asia, Southeast Asia, the Americas, and Oceania are represented by small and patchy samples. A couple dozen crania scattered over thousands of years cannot tell us whether a 10% average shift happened there or when. So when you hear a neat global timeline, human brains started shrinking X thousand years ago everywhere, that's already a simplification. Even the recent widely publicized paper led by Jeremy De Silva, which argues for a sharp decline beginning around 3,000 years ago, is essentially a statistical model built on uneven regional data. Other anthropologists have pushed back, suggesting that earlier declines in some areas and more gradual shifts in others are being blurred together when everything is forced into a single curve. Underneath those disagreements, there is still something interesting. The changes we do see tend to line up with ecology. Climate, latitude, and body size all shape what kind of bodies, and therefore what kind of skulls, tend to do well in a given region. Colder climates with long winters and high latitudes often favour stockier, more compact bodies that conserve heat. Warmer climates, especially near the equator, tend to favour leaner builds that shed heat efficiently. These patterns are well known in biology and show up across mammals, not just in us. Because larger bodies usually come with larger brains, some of the regional variation in cranial volume likely has nothing to do with brain efficiency and everything to do with simple thermoregulation. Late Pleistocene Europeans and some Near Eastern groups were living through intense glacial cycles. They were big-bodied, heavily muscled, often quite robust people, and their brain cases scaled accordingly. As climates moderated, diets changed, and lifestyles shifted, average body sizes in many of these regions decreased. That alone would drag the average cranial capacity downward, even if relative brain size, The brain, compared to the body it's sitting in, stayed the same. Farther south, in warmer, more stable climates, bodies might not have been under the same pressure to shrink or bulk up. That could help explain why some tropical populations show less dramatic changes in raw cranial volume over time. But climate is not destiny, and geography is not neat. For tens of thousands of years, humans have been astonishingly mobile. People moved along coasts and rivers, through mountain passes and across open steppe. Groups split and merged. Traders carried obsidian, shells and pigments over hundreds of miles, and with them went genes, marriages and stories. This constant movement means that any attempt to say brains shrank in region A because of environment X has to deal with the fact that region A has not housed a static, isolated population. Waves of migration bring in people whose bodies and brains evolved under different conditions. Intermarriage blends lineages. Local climate can be pulling one way, while incoming genomes are still tuned to a different set of pressures. Even within a single valley, over a few thousand years, you might see hunter-gatherers giving way to herders, farmers, and then mixed economies that combine fishing, agriculture, and trade. Each shift changes diet, disease exposure, workload, social organization, and mobility, all of which could nudge both body and brain. This is why comparisons between hunter-gatherers and farmers are so tempting and so dangerous. On the surface, they offer a clean contrast. Late Ice Age foragers in many regions look tall, robust, and big-brained. Early farmers, especially in some Neolithic European and Near Eastern sites, often look shorter, more gracile, and on average have smaller cranial capacities. It's very easy to draw a straight line. We settled down, started farming, ate worse diets, got more diseases, and our brains shrank. Pieces of that story are plausibly true. Sedentary farming did bring more infectious disease into human communities. Diets based on a few staple crops can be less nutritionally dense than the diverse wild foods foragers rely on. There is good skeletal evidence of increased stress, anemia, and periodic famine in some early farming communities. All of these could reduce body size and perhaps favour metabolic efficiency over sheer brain volume. But the hunter-gatherer versus farmer dichotomy hides as much as it reveals. Many so-called hunter-gatherers in the Holocene engaged in plant management, seasonal cultivation, and trade. Many early farmers hunted, fished, and foraged extensively. There isn't a sharp behavioural wall between the two categories, and when you compare their skulls, you're rarely comparing matched populations. The foragers and the farmers often lived in different microclimates, used different technologies, and had very different histories of migration and marriage. So when you see a paper claiming that the transition to agriculture caused human brain shrinkage, it's worth reading the fine print. Some of the observed differences probably trace back to diet and disease, yes. Some probably reflect body size changes driven by climate. Some may have to do with social complexity, how information, labour and risk were being shared within and between groups. And some may simply be noise in small biased samples. The deeper you go, the harder it is to pin the change on a single cause. That, in a way, is the point. Brains do not evolve in isolation. They sit inside bodies which sit inside environments which are woven into cultures and technologies and social networks. Multiple mechanisms can be operating at once. Climate nudging body size, diet reshaping growth, social life selecting for certain kinds of cognition, and cultural tools offloading memory and calculation outside the skull. In a moment, we'll look more closely at one of the most intriguing of those mechanisms, the idea that as our societies became more cooperative and less violently competitive, we may have self-domesticated ourselves into gentler faces and perhaps into slightly different brains. Before we go there, if you'd like a slower, deeper dive into this kind of big-picture human story, the book over at sleepytimehistory.com is built for exactly that kind of late-night curiosity, and it's quietly discounted this week. But for now, keep this in mind. There is no single map where you can draw a circle and say, the human brain shrank here for this one reason. What we see instead is a patchwork of overlapping trends, different in timing and magnitude across regions. all hinting that several subtle forces have been shaping our heads at the same time. One of the boldest ideas about those forces doesn't start with climate or calories at all. It starts with temperament. In biology, there's a pattern called the domestication syndrome. When wild animals are domesticated, when humans, intentionally or not, start breeding them for reduced fear and aggression, you don't just get calmer behaviour, you get a whole bouquet of physical changes that tend to appear together. Wolves that become dogs don't just stop attacking you as often, their faces change, the snout shortens, the skull becomes a little rounder, less heavy-browed, more juvenile-looking. Teeth get slightly smaller, ears can flop, body proportions shift, hormone levels change, stress responses soften. If you line up a wolf skull and a dog skull, the shape difference is so striking that you can almost read temperament from bone. Biologists have reproduced this in real time. In the famous Russian fox experiments, breeders selected only the friendliest, most human-tolerant foxes each generation. Within a few decades, the tame line didn't just lick hands and wag tails. Their skulls and faces looked different from their wilder cousins. Shorter snouts, rounder heads, changes in pigmentation and reproductive cycles, all tied into a developmental cascade that seems to turn down the volume on the old reactive stress-driven system. This is where the human self-domestication hypothesis comes in. The basic idea is simple, and also a little unsettling if you're used to thinking of humans as outside nature. Maybe over the last few 100,000 years, and especially in the last 50,000 or so, we've done something to ourselves that looks a lot like domestication. Not because another species was breeding us, but because we were shaping each other's lives. In small, mobile forager groups, in early villages, in the first towns and cities, individuals who were violently impulsive, chronically aggressive, or unable to navigate social rules would have had a harder time. They might have been driven out of groups, denied mates, or quietly killed in conflicts and punishments. People who could cooperate, rein in their tempers and read social cues, on the other hand, would have been more likely to survive, pair up, raise children, and pass on their genes. Over many generations, that kind of social selection could gradually favour what anthropologists sometimes call prosocial traits: reduced reactive aggression, greater tolerance of strangers, more flexible, socially aware behaviour. If something like domestication syndrome operates in humans too, then behavioural shifts of that kind might not stop at behaviour. They might also leave subtle fingerprints in our bones and brains. When researchers compare late Pleistocene skulls, the robust, big-bodied people we met earlier, to more recent Holocene skulls, they don't just see changes in volume, they see changes in shape. On average, faces become shorter from front to back. The brow ridges soften. The mid-face retreats a bit under the forehead instead of projecting so strongly forward. Jawbones become less massive. Overall cranial robusticity, the thickness and heaviness of the bones, declines in many regions. In some samples, the skull vault becomes a little more globular. You can think of this, very loosely, as a drift from wolfish toward doggish, or perhaps more accurately, from Ice Age tough toward Holocene gentle. Alongside these skeletal changes, there are hints of shifts in everyday behaviour. Archaeologists and primatologists talk about rising social tolerance, more individuals from different families, sharing space, food and tasks, more long-distance exchange, more evidence of people living in close proximity without constant violence. Over time, human communities seem to become better at packing more people into the same social world without everything collapsing into feuds. Self-domestication theory knots these threads together and makes a testable, if still fuzzy, prediction. If we have been selecting ourselves, however unconsciously, for lower within-group aggression and higher social tolerance, we should expect our skeletons, and possibly our brains, to show a domestication-like pattern. In domesticated mammals, one of the recurring features of that pattern is a relative reduction in brain size compared to their wild ancestors. Dogs, for instance, have smaller brains relative to body size than wolves. Domesticated pigs have smaller brains than wild boar. Horses, sheep, rabbits. Across many lineages, when populations are selected for tameness and thrive in more predictable social, human-constructed environments, average brain volumes often dip a bit. The leading explanations are not about getting dumber, but about shifting costs and benefits. Wild animals may need bigger sensory and stress management systems to constantly monitor danger and competition. In the safer, more buffered environments that domestication creates, some of that neural real estate becomes less crucial. Energy that would have gone into growing and maintaining large brains can be reallocated to other things: reproduction, immunity, digestion, or more specialized circuits. If humans really did self-domesticate, you might expect something similar: a slight trimming of overall brain volume, even as certain regions reorganize or specialize for dense social life, language, and cultural learning. That is one way to read the late Holocene decline in cranial capacity, not as a sign that we peaked and then slid downhill, but as part of a domestication-like shift toward calmer, more tightly knit, more culturally complex societies. But here we need to be very clear about where evidence ends and speculation begins. Self-domestication is an attractive idea, in part because it seems to line up a lot of things we'd like to fit together: gentler faces, less robust skeletons, growing social complexity, and the observed brain size decline. Some studies have even tried to tie it to specific genetic pathways, especially those involved in neural crest cells, a type of early embryonic cell that contributes both to facial structure and to parts of the nervous system. Still, several big questions are unresolved. One is timing. The skull changes associated with gracilization, lighter bones, shorter faces, start long before the last 10,000 years. They're already underway in some regions by at least 100,000 years ago, and possibly earlier. The brain size decline we've been talking about likely layers on top of a much older trend, which means you can't simply say agriculture made us tame and that shrank our brains. The story would have to be more gradual and more global than that. Another issue is how to measure aggression in the archaeological record. Bones and tools can tell us about injuries, homicide rates, and warfare, but they're silent on everyday temperament. A community might have gentler faces and smaller average brains and still be perfectly capable of organized violence on a large scale. History leaves no doubt about that. There's also debate about whether humans really fit the classic domestication pattern. Some researchers point out that while our faces have shortened, our brain cases during most of our evolution grew larger, not smaller. Others argue that the kinds of selection pressures acting within human societies, gossip, reputation, cultural norms, law, are not the same as the strong, directed breeding that humans impose on animals. And crucially, even if self-domestication is real, it doesn't automatically explain the magnitude or timing of the Holocene brain size changes. It may be one piece of the puzzle, interacting with shifts in diet, disease, workload, and body size rather than replacing them. So for now, self-domestication remains a leading, but not settled, explanation, a lens you can look through that makes certain patterns come into focus without claiming to solve everything. In the next part, we'll pull back from size again and ask a different kind of question. If brains were getting slightly smaller in volume, could they also have been getting better organized, rewiring themselves in ways that made more efficient use of less tissue? When you hear smaller brain, it's almost impossible not to feel that little jolt of judgment. Less must mean worse, less must mean dumber. But the more we look at how brains actually work in humans and in other animals, the less that simple picture holds up. One of the main alternatives is sometimes called the efficiency hypothesis. The idea is that natural selection doesn't just push brains to be bigger and bigger, like inflating a balloon. It also pushes them to be better wired, shorter communication paths, less redundant tissue, more specialized regions, and smarter ways to use the energy available. Because brain tissue, unlike most of the rest of your body, is outrageously expensive. Right now, as you listen, Your brain is only about 2% of your body weight, but it's burning something like 20% of your resting energy budget. It's like driving around with a tiny car that insists on using a fifth of your fuel even when you're parked. In a world where calories were hard to come by, that cost mattered. Every extra gram of brain had to earn its keep. So when we talk about brain size changes in the last 10 or 20,000 years, one way to frame it is not we lost X cubic centimeters, but maybe we paid the same bill in a different currency. Instead of adding more and more raw volume, later humans may have re-engineered what they already had. Neuroscientists today make a distinction that's crucial here: total volume versus organization. Two brains can have the same overall size and very different internal layouts. Or one can be a bit smaller but more intricately folded, more densely interconnected, or more cleverly divided into specialized zones. Take cortical folding, for instance. The way the outer layer of the brain, the cortex, crumples in on itself into ridges and grooves. Those folds aren't just wrinkles for their own sake. They're a way of packing more surface area into the same skull volume, bringing distant regions into closer physical proximity and shortening the wiring between them. More folding up to a point can mean more processing area and shorter communication routes without making the head any bigger. You can also change the relative sizes of different regions. You might shrink some areas that are less critical under new conditions while expanding or reorganizing others that matter more. Language networks, social cognition circuits, planning and working memory systems. From the perspective of evolution, that kind of rearrangement can be more efficient than just inflating the whole structure. Modern brain imaging backs this up in living people. When scientists look for what predicts cognitive performance, they don't find a simple, clean line that says bigger brain, always smarter. There is a weak correlation at very broad scales. Larger brains tend to support more overall capacity. But within normal human ranges, how the brain is wired often matters more than how much total tissue there is. Measures like network efficiency, how quickly information can move between distant regions, how many steps it takes to go from one node in the network to another, turn out to be strongly related to things like reasoning, problem solving, and learning speed. In other words, the internal roadmap matters at least as much as the square footage. We see the same pattern across species. Sperm whales have brains much larger than ours in absolute terms, but they are not building particle accelerators. Some small birds, like corvids and parrots, punch far above their brain volume weight class, solving puzzles and using tools with brains that would look unimpressive on a size chart. Among primates, there's a rough relationship between brain size and behavioral complexity, but it's full of exceptions once you zoom in. The details of connectivity, neuron density, and region-by-region specialization all change how that volume is used. That's the spirit of the efficiency hypothesis applied to our own history. Maybe late Pleistocene humans were running a certain kind of brain, large, expensive, tuned to a particular mix of ecological and social demands, and later Holocene humans gradually shifted to a different design. Slightly smaller in bulk, but more optimized for densely interconnected, culturally saturated, high communication lives. You can imagine it a bit like computer hardware. Early machines got better partly by getting physically bigger, more room for components, more raw power. But a huge clunky machine with poor architecture will lose to a smaller, well-designed system that routes information more intelligently and wastes less heat. At some point, design starts to matter more than size. A shrinking or stabilizing outer casing, combined with smarter internal architecture, could be exactly what natural selection would favor once a species hits a certain threshold of complexity and faces new constraints on energy and development. There's another layer to this. Because the brain is so metabolically costly, any change that allows you to achieve the same or better cognitive performance with less tissue is strongly favored. That could mean finer tuned developmental programs that prune away unnecessary connections more aggressively, or that prevent overgrowth in regions whose jobs have been partly taken over by culture, tools, and social institutions. Over many generations, those savings add up. The spare calories can be redirected into immune function, reproduction, endurance, or supporting more total bodies in a given environment. A slightly leaner, more efficient brain design could mean more surviving children, even if nobody involved ever noticed the difference consciously. All of this makes the efficiency story sound very appealing. It gives us a way to say, maybe smaller doesn't mean worse, maybe it means good enough but cheaper. But here we need to bring in a key limitation. Skulls do not preserve wiring diagrams. From a fossil we can estimate total volume, overall shape, and a few broad features of the outer surface. We cannot see cortical folding in fine detail. We cannot count neurons, and we certainly cannot trace the microcircuitry that actually determines network efficiency. We're inferring a possible reorganization from modern brains, from comparisons across species, and from the fact that selection has powerful reasons to trim excess cost. It's a plausible, even elegant story, but it's still a story. There is some indirect support. For example, studies of endocasts, the internal impressions of fossil skulls, suggest that over long spans of human evolution, certain regions associated with parietal and frontal functions become more expanded and globular. That hints at changing proportions and perhaps changing connectivity. But tying that directly to the relatively recent Holocene volume decline is hard. The resolution of the fossil record is just not that fine. So when you see a plot showing cranial capacity dipping over the last 10,000 years, it's tempting to say, don't worry, the brain probably just got more efficient. That might be true. Parts of it almost certainly are true, in the broad sense that our brains today are embedded in cultural and technological systems that allow them to offload a lot of work. But scientifically, we have to keep the caveat in view. We are working with outer shells, not with circuits. The efficiency hypothesis is a serious contender, not a proven fact. In a moment, we'll put that idea alongside another big piece of the puzzle: what changed in our diet and daily lives as agriculture and settled living spread, and how those shifts might have quietly reshaped the balance sheet between brain size, body size, and the cost of running this energy-hungry organ. And before we go there, this is a good time to mention that if you'd like a slower, more detailed wander through deep time, something you can fall asleep to, there's a new book up at sleepytimehistory.com with a discount running this week. It follows these same themes of human change and adaptation, but at a more drifting, bedtime pace. When you zoom in on the last 10 or 12,000 years, one transformation towers over almost everything else. People stopped moving quite so much, and plants started moving a lot more. In scattered regions around the world at different times and in different ways, human groups began to shift from hunting and gathering wild foods to tending patches of ground, planting seeds, weeding, watering, and waiting. Grasses that had once been occasional snacks became staple crops. Animals that had once been wary game became fenced-in herds. This transition didn't happen overnight. For a long time it was blurred and messy. People who farmed during the growing season might still spend part of the year hunting, fishing, and foraging. But over the millennia, in places like the Fertile Crescent, the Nile Valley, the Indus, northern China, Mesoamerica, and the Andes, something like a pattern emerged. Diets narrowed. A forager's menu might include dozens, even hundreds of plant species across a year: roots, shoots, nuts, seeds, fruits, leafy greens, plus insects, fish, shellfish, and game. It wasn't a constant feast. There were hungry seasons, lean years, and local failures, but it was usually varied. Early farmers, by contrast, often leaned hard on a few domesticated species. Wheat and barley, rice, maize, millets, sorghum, tuber crops like potatoes and yams. If those fields did well, there could be enormous piles of one or two foods, stored as grain or dried roots. If they failed, things got bad quickly. Archaeology and skeletal biology let us see some of the consequences etched into ancient bodies. When you compare skeletons from late hunter-gatherer populations to those of the earliest farmers in the same region, a recurring pattern shows up. On average, the first agricultural villages are shorter, with more signs of stress. Teeth preserve a kind of growth diary. Enamel doesn't remodel once it's laid down, so disruptions during childhood, periods of high fever, malnutrition, or intense physiological stress leave faint horizontal lines called enamel hypoplasias. In many early farming communities, those lines become more common. Bones tell a similar story. Long bones can show stunting if growth was chronically limited. The inner surfaces of some skulls and eye sockets develop porous, spongy patches linked to anemia and infection. Spine and joint changes point to heavy, repetitive labour starting young. None of this is unique to farmers. Hunter-gatherers also got sick, starved and worked hard. But as a broad trend, the shift to agriculture seems to have increased the overall burden of disease and developmental stress in many early villages. Part of that is diet quality. Relying heavily on a single grain can mean plenty of calories, but fewer vitamins, minerals and proteins, especially if the grain isn't processed or combined with other foods in ways that unlock more nutrients. Corn, for example, can lead to serious deficiencies without nixtamalization, the alkaline treatment invented later in Mesoamerica. Another part is density. Packed villages with stored food are heaven, not just for humans but for rodents, insects and pathogens. Waste accumulates. Water sources get contaminated. Diseases that couldn't sustain themselves in scattered mobile bands can thrive and become childhood constants. From the standpoint of growth and development, all of this matters for skulls and brains. Human growth is remarkably plastic. If a child faces chronic undernutrition or frequent illness, the body makes trade-offs. It may slow overall growth, reaching a shorter adult height. It may prioritize vital organs and basic maintenance over building extra muscle or bone. Brain development is buffered. Our biology works hard to protect it, but it is not completely immune. In populations where average stature drops due to long-term stress, you often see parallel reductions in head size. Not necessarily dramatic, but measurable. Smaller bodies come with smaller average brains simply because they're scaling together. This gives one of the most straightforward ways agriculture could have nudged human brain volumes downward without any special selection against intelligence. Early farmers in many places seem to have become slightly smaller, more stressed, more disease-exposed than their hunting and gathering neighbours had been. If you measured cranial capacity across that transition, some portion of the apparent decline could just be the body size story. Shorter people, slightly smaller skulls. That doesn't mean every agricultural society was trapped in a state of malnutrition and misery. Over time, many regions saw improvements. Farmers learned crop rotations, manuring, irrigation and food processing techniques that boosted both yields and nutrient availability. They diversified their fields, adding legumes, vegetables, fruit trees and animal products. Trade networks brought in foods that didn't grow locally. In some later agricultural populations, average stature rebounds and health markers improve compared to the earliest village sites. So we have to be careful not to tell a simple farming ruined us story. Agriculture is more like a radical experiment that went through a long, bumpy learning curve. In the early phases, there is strong evidence that health and growth often took a hit. In later phases, in some places, humans figured out how to make settled life nutritionally and demographically powerful. That complexity is important when we link agriculture to brain size. Some researchers have proposed a fairly direct chain. Agriculture leads to worse diet and more disease, which leads to smaller bodies and brains, which helps explain the Holocene cranial capacity decline. There's probably some truth in that, especially in specific regions and time windows where the skeletal evidence lines up with the archaeological record of early farming. But when people go looking for a clean, global, one-to-one match, it falls apart. Brain size estimates don't drop at exactly the same time everywhere agriculture appears. Some hunter-gatherer populations show declines too, perhaps due to climate shifts, resource pressure or contact with farming neighbours. and in some long-farmed regions, skull measurements stabilize or even tick upward again as nutrition improves. So we're left with a tangle. Agriculture clearly changed the developmental environment. More carbohydrates, sometimes fewer micronutrients, more infections, more work stress in childhood. Those changes can reasonably be expected to nudge average body size and indirectly average brain size. But separating that developmental effect, how big individual people can grow under certain conditions, from deeper evolutionary change in the brain's underlying design is hard. Are we looking at smaller brains because people were growing up under tougher conditions, or because natural selection was gradually favouring slightly leaner, cheaper brains in populations that now lived in dense, complex societies, or both, layered together? The evidence we have so far suggests a mix. Some portion of the Holocene decline is almost certainly tied to shifts in nutrition, disease and growth patterns as agriculture spread. Another portion may reflect genuine evolutionary tweaking of brain and body proportions under new ways of life. Untangling those threads is one of the big challenges in this debate, and it leads naturally to the next piece of the puzzle. If bodies were changing, how much of the brain story is simply about scaling, about keeping this hungry organ in proportion to the frame that carries it? To get a handle on that, we need to talk about something biologists love and most other people never think about: allometry. Allometry is the study of how different parts of an organism scale with overall size. If you lined up a mouse, a dog, and an elephant, you wouldn't be surprised that the elephant has the biggest brain in absolute terms. Big animal, big organs. That's allometry. But here's the key. Organs don't always scale 1-to-1 with body mass, double the body size, and you usually don't double the brain. Brains are expensive, so evolution tends to be careful. Across mammals, brain size increases more slowly than body size. That's why scientists talk about relative brain size, not just how big is the brain, but how big is it for a creature of this size. Humans are extreme on this curve. If you take the brain-to-body rules that fit other primates and plug in a 70-kilogram ape, you get a much smaller brain than we actually have. Our brains are already large for our bodies, even before you worry about small percentage changes. Now fold in the last 20,000 years. The end of the Ice Age didn't just warm the climate, it reshaped human bodies in many regions. Skeletons from late Pleistocene hunter-gatherers often show tall statures and very robust builds, thick cortical bone, broad shoulders, strong muscle attachments. These are people whose daily lives demanded a lot of physical work, long distances on foot, heavy loads, powerful throws. As we move into the Holocene, that picture shifts. It doesn't shift everywhere at the same time or in the same way, but there are recurring themes. In many European and Near Eastern samples, average stature dips from the towering late Pleistocene peaks, then meanders up and down with local histories of farming, climate, and disease. Robusticity tends to decline more steadily. Bones get somewhat lighter, limb shafts slender compared to earlier hunter-gatherers. Similar broad trends appear in parts of Africa, East Asia, and the Americas, with plenty of regional exceptions and detours. So if bodies are getting, on average, a bit shorter and a bit less heavily built, then raw brain size numbers need to be handled carefully. Otherwise, we're comparing a population of tall, thick-boned Ice Age foragers to a population of somewhat smaller, more lightly built Holocene villagers and saying, look, their brains are slightly smaller, something mysterious must have happened. One way researchers deal with this is to calculate what's sometimes called a size-corrected brain measure. There are different technical approaches using body mass estimates from femur head size, adjusting cranial volume by stature, or plugging values into allometric equations based on broader primate data, but the basic idea is the same. You ask, given how big these people were overall, was their brain unusually large, unusually small, or about what you'd expect? When you do that, the picture changes. In some data sets, especially regional ones with good measurements of both skulls and long bones, the apparent Holocene brain shrinkage gets smaller once you control for body size. Instead of a dramatic drop in absolute cranial capacity, you see a more modest shift in relative terms, or sometimes almost none at all. In other words, part of the story really does look like simple scaling. Big Ice Age bodies came with big Ice Age brains. Slightly smaller Holocene bodies came with slightly smaller brains. Once you ask how big for their size, the difference shrinks. This has led some researchers to argue that the whole "our brains have been shrinking" narrative is overblown, or at least oversimplified. They point out that if you graph relative brain size rather than raw volume, humans in the early Holocene and humans today cluster pretty closely. Our brains are still huge outliers compared to other primates once you account for body mass. But, and in this topic there is almost always a but, scaling doesn't wipe the slate completely clean. For one thing, estimates of body mass in the archaeological record are themselves noisy. We're inferring weight and build from bones that have been in the ground for thousands of years. Different methods give slightly different answers. That means different teams can get somewhat different size-corrected brain trends from similar underlying material. For another, even when you use careful conservative methods, some samples still show a residual decline in relative brain size. Not everywhere, not constantly, but enough to keep the puzzle alive. You see cases where Holocene populations have brains that are not just smaller in absolute terms, but a bit smaller than you'd predict even after adjusting for their lighter frames. You also see time slices where body size rebounds, people get taller again as nutrition improves, but cranial capacity doesn't fully follow suit. That doesn't mean there was some dramatic global selection against intelligence. It may mean that over thousands of years under changing diets, workloads, social structures and disease environments, natural selection and developmental constraints were quietly reshaping both body and brain, and not always in lockstep. So a careful synthesis looks something like this. First, a substantial fraction of the observed decline in cranial capacity over the last 10 or 15,000 years probably is linked to changes in body size and build. When humans became on average a bit smaller and less robust in many regions, it would have been surprising if brain volume hadn't scaled down at least somewhat. Second, even after taking that into account, some datasets still hint at additional change in the relationship between brain and body. Not a collapse, not a catastrophic loss, but a subtle retuning of proportions that statistical corrections can't completely explain away. That mix is part of why the debate is so lively. Different scholars weigh the scaling piece versus the residual piece differently. Some emphasize the allometry and see the mystery as mostly solved. Others think the leftover signal is real and important, pointing to evolutionary fine-tuning of brain organization and energy use in increasingly complex societies. We'll come back to that reorganization idea in a moment, but before we do, there's one other ingredient we have to stir into the pot: the way humans began shifting some of the brain's workload outside the skull entirely. By the way, if you like following these quiet technical arguments about how we read the deep past from fragments of bone and measurements and statistics, I go into more depth on exactly this kind of question in the book, over at sleepytimehistory.com. It's written to be the same kind of calm, late-night journey as these videos, and there's a discount running this week if you're curious. Because once you start thinking not just about brain size, but about what the brain is actually doing, and how much of that job we can outsource to culture and tools and writing, the shrinking brain story starts to look very different. Imagine you wake up tomorrow with a mild case of amnesia. Not the dramatic movie kind, just one specific rule. From now on, you have to keep everything you need to remember inside your head. No notebooks, no calendar apps, no reminders, no maps, no recipe books, no search engines. If you can't store it in neurons, you don't get to use it. Very quickly, your life would feel smaller. You'd avoid complex schedules because you couldn't track them. You'd cook the same handful of meals because memorizing dozens of recipes is hard. You'd be much less adventurous about travel because navigating a new city without signs, maps, or GPS is a huge cognitive burden. The point of that thought experiment is simple. Human beings are specialists in not doing everything with the biological brain alone. Cognitive scientists call this offloading. Whenever you put a thought into an external medium, scratch a mark on a bone, tie a knot in a cord, tell someone else so they'll remember too. You're shifting part of the memory and problem-solving load outside your skull and into the world. And this is where the brain shrinkage question takes a subtle turn. Because for most of our evolutionary history, if you wanted information to survive, you had only a few options. You could remember it yourself, teach it to someone else, or encode it somehow in the landscape. A trailblaze on a tree, a pile of stones, a pattern of burn marks from managed fire. As societies became more complex, so did the ways we offloaded. Anthropologists talk about social brains, the idea that a lot of human cognitive horsepower is devoted not to solving physics problems, but to tracking other people, who owes whom a favour, who is trustworthy, who has what skills. In a small band of hunter-gatherers, that already matters, but as group sizes grow and as networks stretch across valleys and rivers, the group itself starts behaving like a distributed mind. One person remembers the detailed astronomy for navigation, another carries rare plant lore, a third is the expert flint napper. No one skull holds the entire encyclopedia. Instead, knowledge is parcelled out among individuals, and the social network becomes a kind of living library. That's social offloading. Memory and expertise are stored in relationships. On top of that, humans layer material memory, physical traces that hold information when no one is present. We don't step straight from bare hands to printed books in a single leap. It's a long, continuous ramp. At the early end, there are very simple external cues. Tally marks carved into bone or antler, regularly spaced notches on sticks, patterned arrangements of shells or beads that likely carried symbolic meaning. In some indigenous traditions, knots in cords track debts or stories. In Mesoamerica, quipus, bundles of knotted strings, were used to record census data, tribute, maybe even narrative information. Later still, clay tokens stand for quantities of grain or livestock. Those tokens get pressed into clay tablets with stylized marks. Over time, those marks evolve into writing that can record contracts, myths, laws, technical instructions. None of these inventions had to wait for our brains to change dramatically. They're cultural solutions, piggybacking on whatever neural hardware was available at the time. But once they existed, they altered the environment in which brains were evolving. Because if you live in a world where dangerous, life or death information exists only in fragile personal memory, then individuals with slightly better raw storage and recall might have a noticeable advantage. Forgetting which plant is poisonous, or when the herds migrate, or how to perform a crucial ritual could kill you or your children. If you live in a world where that information is redundantly stored in elders, in oral traditions, in ritual performances, in tally sticks, in carved symbols on rock, then the selective pressure on any one person to carry everything themselves may soften. Notice the word may. This is not the same as saying, once writing appeared, our brain started shrinking. That would be too simple, and the timing doesn't really match. Most of the brain size decline that De Silva and others talk about seems to begin well before fully developed writing systems became common. But the broader pattern, the gradual building of offloading mechanisms, starts much earlier. Long before cuneiform tablets and hieroglyphics, there were song cycles that encoded navigation routes, mythic genealogies that preserved political claims, seasonal rituals that embedded ecological knowledge in story and performance. These are memory technologies too. They're just embodied in voices and gatherings rather than ink and paper. In that context, you can sketch a cautious, plausible idea. As human societies accumulated more and more external supports for memory and reasoning, as knowledge came to reside in tools, in traditions, in specialist roles, in marks on bone and clay, it might have become slightly less crucial, from a survival standpoint, for each individual to possess the maximum possible volume of neural tissue. Not unimportant. Just a little less unforgiving. If a group can collectively remember 10,000 crucial facts through song, story, ritual and notation, then the fitness cost of an individual whose brain is, say, a few percent smaller but metabolically cheaper might not be as high as it would have been in a purely oral, purely individual memory world. Over many generations in very large, culturally rich populations, that kind of relaxed pressure could, in principle, allow a modest reduction in average brain volume without any obvious drop in functional intelligence. There are important caveats. We don't have a fossil that says, this skull is smaller because tally sticks existed now. Culture doesn't fossilize cleanly, and selection pressures are messy and overlapping. Nutritional shifts, disease burdens, changing workloads, self-domestication, and simple allometric scaling are all in the mix. Offloading is just one more ingredient, and even the offloading hypothesis itself has layers. Some researchers argue that external memory tools actually allowed brains to specialize and become more efficient, perhaps favoring reorganization over raw size. Others think the effect on selection for brain volume would be tiny compared to dietary or life history changes. But if you step back and look at the shape of human history, a species that invests heavily in culture, builds shared archives of knowledge, and constantly stuffs information into tools, symbols, and institutions, it would be surprising if that had no evolutionary consequences at all. It doesn't give us a neat, single-cause explanation for shrinking brains. It does give us a way to think about how the relationship between brain tissue and thinking work has been changing. By the time we reach the Holocene villages and early cities, neurons are no longer the only place important information lives. Some of it is in other people. Some of it is in objects. Some of it is in marks that can outlast any single lifetime. And that sets up the next twist in the story. What happens when humans don't just offload to tools and texts, but start to behave at scale, like parts of a bigger thinking system? Something more like an ant colony than a lone ape with a big head. This is where Andrew De Silva and his colleagues step in with a very particular and very controversial idea. If offloading and social brains are real, they ask, what happens when you scale that up to truly large societies? They point to ants. Individual ants are not, by mammal standards, cognitive powerhouses, but an ant colony can solve surprisingly complex problems. It can allocate workers to where they're needed, adjust for changing food sources, regulate temperature, and defend the nest. The intelligence doesn't live in one ant. It lives in the pattern of interactions among thousands of them. De Silva's team suggests that as human groups grew, something faintly analogous happened. No, we did not turn into ants. There is no queen. There is no hive mind. But as villages grew into towns and towns into city-states, more and more problem-solving moved into the network itself. Shared norms, institutions, division of labour, written records, specialised roles. In their paper, they make an explicit comparison. In small groups, each individual needs a fairly large, flexible brain to juggle many kinds of tasks: hunting, gathering, tool-making, child-rearing, conflict resolution, navigation, medicine. There's not much redundancy. Lose one expert, lose a chunk of knowledge. In large, densely connected societies, the load is spread. Some people can afford to specialize narrowly and deeply. Others can lean on systems, laws, markets, bureaucracies, religious hierarchies that store and process information outside any single head. The colony holds the adaptive intelligence. From there, they propose a bold prediction. As societies become larger and more complex, the average size of individual brains can, in principle, shrink a little without harming overall group problem solving. The costs of maintaining lots of energetically expensive brain tissue might be relaxed, just enough for natural selection to start favouring slightly smaller, metabolically cheaper brains, as long as the social and cultural scaffolding stays in place. In their original work, De Silva and his co-authors tie this to a particular moment. They argue that human brain size peaked in the late Pleistocene and then began a statistically significant decline somewhere around 3,000 years ago, just as states, empires, and fully literate, bureaucratic societies were becoming widespread in some parts of the world. On their timeline, the rise of truly large-scale, institution-rich societies is not just part of the background, it's the key turning point. That's where the ant colony analogy is supposed to bite. As our cultural superorganisms take on more cognitive work, individual brains are under less pressure to be maximally large. It's an elegant story. It brings offloading, social brains, and collective intelligence together into one tidy narrative. And a lot of researchers think the narrative, as a general framework, is at least worth taking seriously. The idea that big dense societies might shift selection pressures on individual cognition is not wildly implausible. We know institutions can buffer people from certain risks and amplify others. We know that division of labour can let some skills atrophy while others sharpen. We know that information can be stored and processed outside the brain, but the moment De Silva's team put concrete dates on the decline, the pushback started. Other anthropologists and paleoneurologists took a close look at the dataset and the statistical methods and raised several concerns. One issue is sampling. The fossil and skeletal record is patchy and uneven. Some time periods and regions are overrepresented, others barely appear. If you're not careful, it's easy to mistake a shift in where your specimens come from for a genuine global trend. Another issue is timing. Several critiques argue that when you adjust the sample or use different ways of binning the data, the sharp late Holocene drop around 3,000 years ago becomes much less clear. Some analyses suggest the main decline may start earlier. Others find that once you control for body size and other factors, the apparent recent cliff mostly flattens out. Body size itself is a major confound. Humans have not been the same size everywhere or at every time. Diet, disease, workload, and climate all shape stature and build. Because bigger bodies tend to have bigger brains. At least up to a point, you have to correct carefully for changes in body size before you claim a genuine shift in brain-to-body scaling. Several critics argue that De Silva's team didn't do this robustly enough, and that some of the observed pattern might simply reflect smaller bodies in certain late samples. Then there's method mixing. The dataset combines endocasts from ancient skulls, direct cranial measurements, and modern imaging studies. Each of these has its own quirks, error margins, and biases. If you treat them all as directly comparable, you might introduce spurious trends. Some researchers have called for cleaner, method-consistent datasets before we draw strong conclusions about exactly when the decline began. Because of all this, the specific claim that human brains started shrinking around 3,000 years ago as states and complex societies rose is now very much an open question. It hasn't been decisively falsified, but it has been sharply challenged. Different groups, using different samples and models, get different answers about the timing and steepness of the drop. That doesn't mean the whole ant colony line of thought goes in the trash. Even researchers who are skeptical of the exact timing often agree that the broader idea that large organized societies can change selection pressures on brains is worth exploring. The insight that cognition is partly distributed across social networks and material culture remains powerful, independent of whether the main decline starts 3,000 years ago, 7,000 years ago, or in several waves tied to different ecological and cultural shifts. The De Silva hypothesis has also done something else valuable. It has forced people to sharpen their questions. How reliable are our cranial data sets, really? How do we best correct for body size, sex, geography, and taphonomic bias? Are there regional differences in brain size trends that get blurred when we average everything together? How do we map archaeological evidence of social complexity onto biological changes with any confidence? Those are the kinds of questions that drive a field forward. Science, especially about deep time, rarely moves by grand, final debunkings. It moves by proposals, counter-analyses, refinements, and new data. A hypothesis can be wrong in its details and still be useful in the way it rearranges our thinking. While this debate is playing out, everyday science continues, New measurements of old skulls, better imaging of museum collections, improved statistical models, and more careful reconstructions of past body sizes. And this is a good moment to pause, take a breath, and remind you that if you enjoy this kind of slow, evidence-based untangling of human history, there's a whole book of it waiting at sleepytimehistory.com. It walks through other puzzles like this, in the same calm, curious way. And there's a discount on this week if you want to explore further. When we come back to our shrinking brains, the key takeaway from the ant colony debate is not that we've solved the mystery, or that someone else's favourite theory has been vanquished. It's that brain size is probably shaped by a tangle of forces: diet, disease, body scaling, self-domestication, life history, and yes, the growing power of collective intelligence. The ant colony argument gives us one more lens to look through, but to understand what shrinking brains actually mean for thinking, for creativity, for everyday life, we have to turn from how big they are to how they're organized. So let's sit for a moment with the anxious question that tends to float under all of this. If our brains have, on average, become a bit smaller than those of late Pleistocene humans, does that mean we're getting dumber? The evidence, as far as we have it, says no. First, volume is a very blunt instrument. It's like trying to judge how good a library is by measuring the size of the building from the outside. You'll get a rough sense of capacity, but you won't know how the shelves are arranged, how up-to-date the books are, or how good the cataloguing system is. When neuroscientists look at modern humans, brain size explains only a modest slice of the variation in test performance between individuals, and that's within the same population, under the same nutrition, education, and health conditions. Some very capable people have below-average brain volumes. Some people with larger brains struggle. Intelligence, whatever exactly we mean by it, is multidimensional: working memory, pattern spotting, verbal fluency, spatial reasoning, social perception, creativity, long-term planning. These don't all rise and fall together in lockstep with cubic centimeters. On top of that, brains are plastic. They rewire themselves in response to use. A child who grows up juggling multiple languages, dense social environments, and complex tools, anything from musical instruments to software, will see networks in their brain strengthen and prune in ways that no fossil can record. Education, training, nutrition, early life stress, sleep, toxins, trauma all leave their fingerprints on real living brains in ways that swamp the tiny differences we're talking about in average cranial volume over thousands of years. And then there's culture. A large part of what we casually call intelligence is actually cultural performance, how well you navigate the specific tools, symbols, and expectations of your own society. A late Pleistocene hunter might have outperformed most of us in tracking game, reading subtle landscape cues, or making stone tools under pressure. A modern teenager dropped into their world would look bewildered and incompetent for a long time. Reverse the experiment, though, and that Ice Age hunter, dropped into a 21st century city, would face an equally steep learning curve. They'd be surrounded by layers of technology and institutionally stored knowledge that didn't exist for their ancestors. Written laws, digital media, mass education, modern medicine. The ceiling on what a human mind can learn and do is now scaffolded by a huge cultural superstructure. So when we talk about shrinking brains, we're not talking about a simple, automatic, one-dimensional decline in some raw, generalized mental horsepower. We're talking about subtle changes in anatomy sitting on top of an enormously powerful, socially built learning system. And that opens up a very different perspective on natural selection. Big brains are expensive. They demand lots of energy, especially during growth. They make childbirth more dangerous. They require prolonged childhoods and long periods of parental investment. If evolution can maintain the same, or even better, cognitive performance with slightly less tissue, that's a win. Imagine two brains with the same functional output for the challenges that matter in a given environment. One is a bit bulkier and costs more calories to run. The other is slightly smaller but more efficiently wired, with better blood flow, more compact pathways, or just less redundant tissue. Over many generations, if those two designs perform equally well in real life, selection can favour the cheaper option because the saved energy can be spent on immune function, reproduction, or surviving lean seasons. This kind of optimization doesn't require any drop in capability at all. It's less like making the engine weaker and more like tuning it so you don't waste fuel. What we absolutely don't see in the scientific literature is clear evidence of a global, recent collapse in human cognitive abilities driven by biology, a downward spiral in innate intelligence mapped neatly onto brain volume. Performance on many forms of formal testing has actually improved over the last century in several countries, likely because of better nutrition, education, and more cognitively demanding environments. That trend, often called the Flynn effect, is itself complicated and uneven, but it's the opposite of the simple "we're getting dumber now" story. This is why scientists are very cautious about how they talk about shrinking brains. Claims that modern people are less intelligent than our ancestors slide very quickly into narratives about degeneracy, decline, and who is supposedly more or less evolved. Those narratives have a long history of feeding eugenics, race pseudoscience, and all kinds of cruel policies. They also ignore the basic population, genetic reality, that most human variation in cognition is within groups, not neatly between them, and that our species remains one interbreeding, globally mixed population with extremely shallow genetic differences. Nothing about the observed changes in average brain volume supports ranking whole populations in terms of worth, destiny, or moral value. Nothing about it justifies treating some people as throwbacks and others as advanced. Those are social stories people layer on top of data, not conclusions that come out of the measurements themselves. So what does shrinking mean in a way that's actually useful? It tells us that there has been a shift in the balance of evolutionary pressures acting on our anatomy. Something about our diets, our disease environments, our life histories, our social structures, or all of these together made it possible and perhaps advantageous for average brain volume to drift downward from its late Pleistocene peak without obvious catastrophe. It points us toward trade-offs between metabolic cost and capacity, between individual versatility and social specialization, between redundancy in one head and reliability in the network of heads around it. The puzzle is not a judgment on modern humans. It's a question about how evolution reshapes a species that has moved from small precarious bands on the edge of survival to large interdependent societies saturated with tools, symbols, and institutions. When we keep that in mind, the shrinking doesn't say, "You are less than your ancestors." It says, "Your ancestors and you are part of an ongoing experiment in how to build minds, single minds, shared minds, and everything in between, under changing conditions." And the experiment isn't over. To see that, we only have to look at the rest of our bodies and at the ways natural selection has been quietly working on humans right up to the present. If you zoom out a little, the shrinking brain just becomes one thread in a much larger pattern. Because humans didn't step outside of evolution when we invented agriculture, or writing, or smartphones. We just changed what evolution was aiming at over the last 10 or 12,000 years. The stretch scientists call the Holocene natural selection has been nudged and twisted by something new in the history of life. Culture that changes faster than genes can mutate. Picture evolution before that. For millions of years, most of the pressures on our ancestors were set by ecosystems that moved slowly. Climate cycles took tens of thousands of years to rise and fall. Predator communities shifted over geological time. Forests turned to savanna and back again on a timescale no individual could perceive. Then suddenly there's us. Groups of Homo sapiens start clearing land, storing seeds, domesticating plants and animals, building permanent settlements. Disease environments shift as people live closer together and closer to livestock. Diets change as hunting large game becomes less central, and grains, dairy, and processed foods become more common. Every one of those cultural choices feeds back into biology. If your community raises cattle and drinks milk, People with gene variants that let them digest lactose as adults get more calories more reliably. Over a few thousand years, those variants spread. That's why some populations today have high rates of lactase persistence and others don't. It's a clear example of what biologists call gene culture coevolution. Our habits create new selective pressures which change our genes, which in turn shape what habits are possible. The same kind of feedback loop shows up all over the Holocene. High-density farming villages are perfect breeding grounds for pathogens. So genes that tune immune systems to handle measles, smallpox relatives, or malaria get a boost. Cities create new risks of crowding stress and new benefits to social skills. Gossip management, conflict resolution, the ability to navigate hierarchies. Trade and long-distance travel move both people and germs across continents, rewarding some kinds of resistance and vulnerability, some temperaments and life strategies over others. Technology matters too. If your survival depends mainly on your own ability to track game, napstone tools, and remember every water source within 100 miles, the selection pressures on your nervous system are one kind of thing. If your survival depends on fitting into a vast division of labor machine, where you specialize in one task and trust strangers for almost everything else, that's another. In those later settings, brains aren't doing less. They're just doing different work. More time is spent parsing language, norms, numbers and symbols. Less time is spent memorizing every contour of the landscape, or keeping mental inventories of every edible plant in a biome. Written records, maps and institutions take over some of that load. Natural selection can then tolerate or even favour slightly cheaper brain tissue as long as the overall system, the individual plus their cultural scaffolding, still solves the problems of survival and reproduction. Diet shifts play into this as well. Early agricultural diets were often less diverse and less nutrient-dense than those of foragers. More carbohydrates, less protein, more seasonal shortages, more reliance on a few staple crops that could fail together. Skeletal remains from early farmers sometimes show stunted growth, enamel defects, and signs of chronic stress compared to their hunter-gatherer neighbours. Under those conditions, a brain that can reach adequate function with slightly fewer resources might have an advantage, especially if social structures, extended family, villages, ritual networks help buffer individuals against catastrophe. Disease, diet, technology, and social density all tangle together. None of them, alone, has to be huge. Small shifts, a bit more infectious disease here, a bit less protein there, a bit more reliance on external memory in the form of stories, tally sticks or writing can add up over hundreds of generations. At the same time, selection didn't stop tinkering with the rest of our bodies. Genes for high-altitude adaptation became more common on the Tibetan Plateau and in the Andes, letting people thrive in thin air. Variants affecting skin pigmentation shifted as populations moved into different latitudes. Resistance to specific diseases like malaria shaped blood traits in West Africa, the Mediterranean, and South Asia. Even traits like the age of first reproduction and how long people stay fertile have been nudged by changing social and ecological realities. When you put all this next to the brain size story, a particular picture emerges. It's not that something went wrong and our brains started withering. It's that the entire set of trade-offs facing human bodies and minds was rearranged by culture. The value of raw, individual, general-purpose capacity relative to specialized, socially distributed capacity may have changed. The balance between energy spent on neurons versus energy spent on immune defenses or reproductive output may have shifted, and a small, measurable decrease in average brain volume could easily be one visible marker of that deeper rebalancing. None of this means scientists have a tidy, closed-form answer. There's active debate about when the trend began, whether the drop is as large as some early papers suggested, and how much of it is explained by changes in body size, measurement bias, or sampling. The De Silva timing claim, placing the main decline very recently, has pushed people to re-examine datasets and offer alternative interpretations. That's the scientific process doing its job, not a sign that there's a secret story being hidden. What almost everyone in the field does agree on is the underlying principle. Humans never stepped off the evolutionary treadmill. We just started rearranging the track under our own feet. Our ancestors weren't static, perfect models that we've fallen away from. They were people living through their own experiments under their own shifting pressures. The late Pleistocene brain peak, the Holocene decline, the local adaptations layered on top of both, they're all chapters in the same story of a species that keeps rewriting the rules of its own existence. And that story is still being written right now. Even today, fertility patterns, migration, urbanization, and medical technology are shaping which genes are passed on, and in what combinations. We don't know exactly where that will lead, or how our descendants' brains will compare to ours in size or structure. But we can be confident about one thing. The idea that humans have stopped evolving is a myth. By the way, if you enjoy this slower, zoomed-out look at our deep history, there's a book that goes even deeper into these themes over on sleepytimehistory.com. It follows the same gentle evidence-first approach as this channel, and there's a discount running this week if you want something to fall asleep to that, still respects your curiosity. For now, though, we should circle back to our original puzzle. If evolution has been quietly working on us this whole time, if culture and genes have been dancing together through the Holocene, and if shrinking brains can fit comfortably inside that framework, what exactly is left unexplained? Quite a lot, as it turns out. For all the complexity and debate, there is one piece of this story that's surprisingly solid, across independent research groups, across continents, and across multiple kinds of evidence. Actual skulls, digital endocasts, large museum collections, the same basic pattern keeps turning up. If you take adult human crania from the late Pleistocene, say 40 to 20,000 years ago, and you compare their average brain volumes to those of more recent Holocene populations, the older samples tend to be larger. The exact numbers shift, depending on which bones you include, how you correct for sex and body size, and which time slices you compare. Some studies find a drop of around 5%. Early work suggested closer to 10. Newer analyses sometimes shave that back down again. But the direction of the trend, bigger, then smaller, has so far refused to go away. So that part of the shrinking brain story is not built on a single dramatic dataset or on one lab's method. It's the convergence of many partial, imperfect lines of evidence. Where things get murkier is everything around that central line. We still don't agree on the exact timing. One camp, following people like Jeremy De Silva, argues that most of the decline is surprisingly recent, within the last few thousand years, even overlapping with the rise of complex societies. Others push back and say no, the main change is earlier and more gradual, starting closer to the Pleistocene-Holocene transition and stretching over 10 or 15,000 years. Some analyses hint at plateaus and step changes rather than a smooth slide. Others argue those bumps are artifacts of how the samples are binned. Right now, the data simply aren't dense enough in time to let us draw a clean, continuous curve. Regional patterns are also unsettled. Were brains shrinking everywhere at once? Or do we see different trajectories in Europe, Africa, Asia, the Americas, Oceania? The global human story over the last 10,000 years has been anything but uniform. Agriculture arrives at different times in different forms. Some groups remain foragers well into the historical period. Climatic shifts, disease environments, population densities, and diets all vary wildly from place to place. If brain size is responding to those local conditions, as we would expect, then we shouldn't see a single worldwide curve. We should see a patchwork of curves, some steeper, some flatter, some maybe even reversed for a while. There are hints of that in the existing literature, but the samples are frustratingly uneven. European and Near Eastern crania are heavily represented. Other regions, especially large parts of Africa and much of the Americas, are still undersampled. Until that changes, any global average is hiding a lot of detail. And even if we pinned down the timing and geography perfectly, the hardest question would still be waiting. What exactly is driving the change? We've walked through some of the main suspects: body size, self-domestication, diet, disease, the offloading of memory and problem-solving into culture and technology. Each of them is plausible. Many of them are supported by independent lines of evidence. None of them, on its own, quite feels like the whole story. Body size corrections reduce the apparent brain shrinkage, but don't always erase it. Self-domestication explains face shape and some behavioral trends, but the link to brain volume is indirect. Diet clearly mattered, but nutritional stress doesn't always correlate neatly with brain size in the fossil record. Cultural scaffolding almost certainly changed what brains were asked to do, yet we don't have a direct way to measure that demand in ancient populations. Most likely, we're looking at a bundle of interacting pressures, shifting at different times in different places. But which combination matters most, and when, is still an open question. So what would actually move us from speculation to something firmer? One key piece is just more and better measurements. Larger, more geographically balanced cranial datasets, analysed with consistent methods, would help nail down both timing and regional variation. Three-dimensional imaging of skulls, combined with refined techniques to estimate soft tissue volume, can reduce some of the uncertainties that come from older, more approximate methods. Better controls for body size are crucial too. That means not just rough stature estimates, but detailed reconstructions of overall build. Maybe even using new statistical models that combine skeletal dimensions with modern comparative data. The tighter we can lock down the relationship between brain volume and body mass in each sample, the clearer any residual brain-specific trend will become. On the living human side, modern brain imaging offers a different angle. Large-scale MRI studies can map how brain volume, cortical thickness and connectivity patterns vary with lifestyle, diet, education and health in present-day populations. Those correlations won't directly tell us what happened 10,000 years ago, but they can constrain what's plausible. If certain environmental factors consistently shape brain structure today, they become more credible candidates for shaping it in the past. Genetics is another frontier. As ancient DNA work accelerates, we're beginning to see not just who was related to whom, but which gene variants related to brain development, metabolism, and plasticity were present in different times and places. Over the next decades, it may become possible to trace how alleles affecting skull shape or neural growth changed in frequency through the Holocene, and how those trajectories line up with the anatomical record. Archaeology and cultural history round out the picture. The more precisely we can date the spread of particular farming systems, urbanization, writing, schooling, and complex division of labor, the better we can line those cultural shifts up against any biological trends. Was a local downswing in brain volume already underway before intensive agriculture arrived? Did it accelerate with the rise of cities, or with new disease loads, or with the spread of particular technologies? Right now, those alignments are mostly sketched in broad strokes. Finer chronology could reveal patterns we simply can't see yet. Underneath all of this is a simple, slightly unglamorous truth. We're still in the middle of the investigation. The shrinking brain story is not a tidy mystery box with a hidden answer scrawled on the underside. It's a live scientific debate with new skull measurements, new radiocarbon dates, new genetic sequences, and new statistical methods trickling in every year. Claims get made, challenged, revised, or sometimes quietly abandoned when better evidence shows up. That back and forth isn't a sign that something is being concealed. It's the normal way knowledge grows, especially when the evidence is old, fragmentary, and hard to interpret. So for now, we live with a set of layered certainties and uncertainties. We can be fairly confident that average human brain volumes were higher in the late Pleistocene than in much of the Holocene. We can be fairly confident that humans have continued evolving under the intertwined pressures of culture, ecology, and biology. We can be fairly confident that any story about decline or improvement is far too simple for a system as complex as a human brain entangled in a human society. Beyond that, the details are still coming into focus. And that's not a defect in the story. It's part of its texture. The fact that we don't yet know exactly why our brains have been shrinking or exactly what that shrinkage means is an invitation to keep measuring, keep comparing, keep thinking carefully about how minds and cultures co-create each other over deep time. It leaves us, in other words, in a quiet, ongoing conversation with our own past. In the last part of this video, we'll lean into that feeling a bit more and let the question stay open. What does it mean to be a species whose history is still being written, even inside our skulls? So here we are, at the edge of what we know, looking back over a very peculiar fact. For at least 10,000 years or so in many parts of the world, the typical human skull has gotten a bit smaller on the inside. Not collapsing, not melting away, just quietly trimming volume around the edges. The measurements are real enough to take seriously. The reasons are still slipping through our fingers. The best candidates we have form a kind of loose circle around the puzzle. Some of it almost certainly has to do with bodies, changes in average height, build and energetics as diets, workloads and disease environments shifted after the Ice Age. Some of it looks like self-domestication, the long, slow favouring of calmer temperaments, rounder faces and less reactive nervous systems in more crowded, more governed societies. Some of it points toward food and farming, new grains, new deficiencies, new constraints on how much costly tissue the body can afford to maintain. Some of it may come from what we asked brains to do. As more information moved into stories, rituals, writing and tools, fewer things had to be remembered or simulated directly in neural tissue. Culture and technology took on more of the load. None of these forces cancels the others. They layer, they interact. They probably do so differently in different regions at different times. And yet, even with all of that in play, one thing this story does not say is that we have become less human. A smaller average cranial capacity is not a downgrading of our species. It is not evidence that people in the deep past were better or that people now are somehow diminished. The abilities that matter most for real lives, language, empathy, creativity, cooperation, the sheer strangeness of human imagination, don't track cleanly with the raw size of the brain case. Over the last 10,000 years, while those average volumes were nudging downward, humans were also inventing mathematics and music theory, building observatories and novels and legal systems, mapping the globe, sequencing genomes, and recording lullabies. Whatever is happening under the skull, the story of our minds is still one of staggering range. So you can let this fact rest in your thoughts without turning it into a verdict. It's a clue, not a sentence. A small curved piece from a jigsaw puzzle that nobody has finished yet. If you've enjoyed drifting through this question tonight, it helps the channel a lot if you gently tap like and subscribe so you don't miss the next deep time mystery. And if you feel like saying hello, I'd love to know where you're listening from. Leave a comment with your city or just your corner of the world. If you'd like to wander further into these prehistoric stories, there's a book waiting for you full of bottlenecks and vanished cousins and quiet revelations from the fossil record. You can read more about it and pick up a copy at sleepytimehistory.com. As you settle in, you might let one last question float at the edge of sleep. If the shape and size of the human brain can change across thousands of years, and if our cultures and tools and stories are always reshaping what those brains are for, then what, exactly, is it that stays the same when we say human? You don't have to answer it now. You can just carry it with you, softly, into the dark, and let your own very modern, very ancient brain do what it does best, wander, dream, and keep evolving, one quiet night